In the last lecture, we saw how to distinguish between concave mirror, which is the inner reflecting side, and convex mirror, which has the outer side as reflecting side. We also defined the focal length of mirrors. We saw how the images are formed by a concave mirror, and we derived the mirror formula. We derived the relation f is equal to r by 2, and we derived this relation 1 by v plus 1 by u plus 1 by f using the sign convention. And we also studied how the location of the image changes as the location of the object changes with respect to the mirror. So, we continue with this, and we shall, in the examples that we studied in the last lecture, that the sizes of the images, they are different with respect to the size of the object. Therefore, we define a quantity called magnification. Magnification is the ratio, the magnitude of the magnification is the ratio of the height of the image divided by the height of the object, h I by h o. The sign of m is determined by the signs of h I and h o. You see, I told you, remember the convention, all distances measured upwards are positive, all distances measured downwards are negative. So, if h I and h o have different signs, then m will have a negative sign. If they have the same sign, minus minus or plus plus, then magnification is positive. So, the sign of magnification would be determined by the signs of h I and h o, and m is called the magnification of the device, say mirror or lens, and m is negative for a real image. Why? Because in the real image, the image is inverted with respect to the object, and therefore, m carries a negative sign. If the image is virtual, then we have seen that it is erect, it is in the same direction, and therefore, the two have the same sign, and therefore, m is positive. Here again, I will just to convey the ideas, this is the object, its height from the axis is h o, this is the image, its height from the axis is h I, and you can compare the triangles, I mean this is simple, and you can get m is equal to h I by h o, the magnitude, and the sign would be negative because the image is measured downwards, the object is measured upwards, they are in the, this is positive, this is negative, therefore, the ratio would be negative. So, magnification is minus v by u, which you can get by comparing the appropriate triangles. So, let us take an example. The real image of a candle is 3.2 centimeters long and is located at 12.4 centimeters in front of a concave mirror of focal length 9.8 centimeters. So, calculate the position of the object and its size. So, we are given v is minus 12.4 because it is a real image and it is toward it, distances must be measured towards the right. Therefore, it is minus 12.4, f for a concave mirror is negative. So, minus 9.8, and we shall find u by the formula 1 by v plus 1 by u is equal to 1 by f, and if we use the signs here of v and f, then we get 1 by u is 1 by v minus 1 by f. So, we substitute the values. How do we substitute the values? That from the mirror equation yielding u equal to 46.7 centimeters. So, we have got u, we have got v, and v by u is the magnification, and this is the actual length. So, it is magnified by the factor called magnification, that is 46.7 divided by 12.4, and therefore, the roughly 4. So, the image would be 4 times 3.2, that is 12.1 centimeters, and this will be a virtual image, and therefore, the magnification is positive. Concave mirrors are used in large optical telescopes. I told you earlier, concave mirrors are used for shaving kits, for makeup kits for women, and by dentists to examine your teeth and so on. They are also used in large optical telescopes. You see, these days telescopes, large telescopes are not made from lenses, and therefore, they use the reflecting mirrors. Large lens, why are large lenses not used? Because large lenses are quite heavy and mirrors are very thin and therefore, not very heavy. Moreover, refracting telescopes need long tubes, which not only add to the weight of the telescope, but also create problems like thermal currents in that. If you have a long tube, there can be temperature gradient and therefore, there can be thermal currents. So, modern telescopes use several small mirrors linked by computers to act as a very large mirror. I will show you example. You see, these are small mirrors, hexagonal mirrors, and they are joined, and we use the computer software to align the images formed by or synthesize an image formed by the individual mirrors. So, this gives a large mirror. These small mirrors, which are easy to make, they are combined by computer software to give a large mirror. A reflecting telescope, therefore, has this ray diagram. The rays come from infinity, from a star or whatever other objects are there, and they get reflected at the concave mirror called the primary mirror. They get reflected, and then there is a secondary mirror here, which is a plane mirror, and this plane mirror, after reflection, the rays go through this lens, which is called the eyepiece, and after passing through eyepiece, they become parallel. The eyepiece is so arranged that the rays become parallel and they enter the eye. So, this is how the rays come from infinity and actually enter the eye after getting reflected at the primary and the secondary mirrors. In the case of radio telescopes, radio waves are also electromagnetic waves. Therefore, like light, they can also be reflected, but they are not reflected by the glass mirrors or glass lenses. They are reflected by solid or metal dishes. You have a metal dish, and this metal dish will reflect the electromagnetic radio waves. So, here we have a dish made of metal, and these are the rays coming. They meet at this point, this mirror here, and this sends them back to this, and there is a detector here housed in this building. Metal dish is used because radio waves are reflected by metal dish. Here is an example of a metal dish and the focal point, and here is the assembly which either detects or sends rays elsewhere. This is the photograph at the right, shows one of the dishes of the giant meter wave radio telescope near Pune, and this was built by the National Center for Radio Astrophysics, which is under the Tata Institute of Fundamental Research. Here also we do not have one single dish, we have large number of dishes, and the image by these dishes is synthesized by computer software to form the final image. This image is taken from NCRA TIFR.S.in. So, having studied the concave mirror, let us come to the convex mirror. Convex mirror, you remember, the reflecting side is outside, the outer side is the reflecting side. We still have P, the pole, and parallel rays, they come and they get reflected in this direction. That means, they appear to come from this point F. Parallel rays, after reflection, they appear to come from the point F, appear to come. Therefore, this P f is the focal length and C is of course, the center of curvature. So, C gives the normal to the mirror, and this angle of incidence is equal to this angle of reflection. This angle of incidence is equal to this angle of reflection. So, the laws of reflection are obeyed, everything, and the rays appear to come from the point F after reflection. So, according to our convention, P f is positive. The focal length of a convex mirror is positive, because it is measured in the direction of the incoming light. The light is coming from the left, this distance is also measured from left to right. Therefore, this is a positive distance. So, focal length of a convex mirror is positive according to our convention. Let me also point out that in several books you will find different things, they might use different conventions, and therefore, we take it positive, some books may be taking it as negative. So, therefore, my suggestion is that we stick with the convention that we use, and then you will get consistent answers to all your questions. The rule for drawing the diagram remains the same. There is no actual rule, there is just one rule, and one rule is because of reflection, angle of incidence must be equal to angle of reflection. So, that is the one rule. So, this ray gets reflected in this direction, this ray gets reflected in such that the angle of incidence is equal to angle of reflection. So, what happens is that this ray, as we have seen, appears to come from F. This ray, which is going to pass through the center of curvature, is normal to the mirror, therefore, there is no deflection. The angle of incidence is 0, angle of reflection is also 0, because this is normal to the mirror. And this third ray comes to P and gets reflected, this angle of incidence is equal to this angle of reflection. So, we have got 3 rays, and wherever these meet, that is the image of this tip of the object. In fact, we do not need to draw all the 3 rays, any 2 rays would do, whichever are convenient. So, once again, let us see how the image is formed. We have the object here, this tip sends 2 rays, one goes like this through C, therefore, there is no deflection. The other goes to P and gets reflected according to the laws of reflection, and these 2 rays appear to meet at this point. So, this tip is the image of this tip, and this is the image of this object. That is how the rays are traced and the images are formed. Remember that I have been telling you again and again that according to our convention, light comes from the left. Whenever we draw ray diagrams, remember that light comes from the left, because we are going to give signs to the various distances. If this is not the requirement, if you just want to show something, then the light may come from any direction. To get the relation between the object distance u and the image distance v and the focal length, we use the same thing that we did earlier. Remember, these are paraxial rays, therefore, these angles alpha, beta, gamma, they are small angles. So, that they are proportional to 1 by u, 1 by v and 1 by r. So, using again geometry, I can write 2 I, this angle is equal to this angle plus this angle alpha plus gamma, and gamma is equal to this angle gamma is equal to beta plus I, this angle is equal to that angle, and therefore, beta plus I is equal to the exterior angle gamma. So, gamma is beta plus I. I shall once again eliminate I from these 2 equations, and we get the relation gamma 2 beta plus alpha. Gamma is proportional to 1 by v, gamma is proportional to 1 by v, alpha is proportional to 1 by u, beta is proportional to 1 by r. So, we substitute these values and we get 1 by v minus 1 by u is equal to 2 by r. Once again 2 by r is equal to 1 by f by the same argument that we gave earlier, and because f is the half of the radius of curvature, we can even formally also prove that. So, 1 by v plus 1 by u is equal to 1 by f. Why is it plus sign here and negative sign here? Because u is negative, u is measured in this direction to the right, and therefore, u is negative, and therefore, we get this sign gets plus. So, 1 by v plus 1 by u is equal to 1 by f. This is the again mirror formula or mirror equation, and you recognize this as the same as in the case of concave mirror. There is no difference in the formula. All the difference lies in assigning the signs to u, v and f. And magnification also retains the same definition. In this case, magnification is positive because both h 0 and h I, they are in the same direction. Therefore, the magnification is positive. So, let us take an example. Suppose the object is at a distance of 60 centimeters in front of a convex mirror of focal length of magnitude 15 centimeters. Where would the image be? Now, obviously, u is in front of the mirror, therefore, it is negative. F we have seen for a convex mirror is positive. We substitute the values and find v, and v turns out to be 12 centimeters and 12 plus 12 centimeters. That means, the image is on the side opposite to that of the object. Once again, the object is on this side, the image is on this side. So, therefore, the image distance turns out to be positive, and magnification is again, if we know the sizes of two things, we can find the magnification, or V by U gives us the magnification, which in this case is 1 by 5. This is important thing to remember. For a convex mirror, the image is always smaller in size. Wherever the object is, the image is always smaller in size. It is virtual and erect and always smaller in size. And this is another example. You can solve this. I have a scale here 30 centimeters long. So, I form the image of this point, which is here, then I form the image of this point, which is here. So, this is the virtual image of the scale, just 2 centimeters. This 30 centimeter scale has an image which is only 2 centimeters. So, the image formed by a convex mirror is always smaller in size. Now, how do we make use of this fact? We define something called field of view. What is field of view? Field of view or field of vision may be defined as the area from which rays can be processed to reach our eyes. The rays, only this region, the rays coming can come through the device and reach our eyes or the detector here. Rays coming from here cannot, rays coming from here cannot. So, only in this area the rays can enter and get detected. So, this is therefore called the field of vision or field of view. So, this is the field of vision or field of view of a camera. What about a plane mirror? If our eye is here, then we can detect only this ray, not this ray, because then after reflection the angle of incidence will not be equal to angle of reflection. So, the maximum that we can get is this ray and this ray. So, therefore, this will define the field of view for this position of the eye. If the position of eye changes, then the field of view will also change. If the eye is here, then only these rays, all rays in between them can reach the eye. These rays which are outside cannot reach the eye, and therefore, they are not part of the field of view of the eye. For a convex mirror, what happens? If our eye is here, then according to the laws of reflection, if the light comes from here, after reflection this will go to the eye. Similarly, a ray coming from here, after reflection will go to the eye. So, therefore, field of view of a convex mirror is much larger than the field of view of a plane mirror, and therefore, we have on the sides of the driver in a car or in a bus or in a scooter a convex mirror, so that its field of view is large, it can show the whole traffic coming behind us and we can drive carefully and properly. There is another thing also. If you carefully see the convex mirror by the side of the driver, there is something written on it, and that is, they say that objects in the mirror are closer than they appear. I can see the whole traffic, but the objects that I see in the traffic are actually much nearer than they appear, right. So, this warning is there. Why is this warning there? Let us see. The driver and passenger side mirrors bear the warning, objects in mirror are closer than they appear. See, nowadays there are two such mirrors. One is by the side of the front passenger, the other is by the side of the driver. So, that the driver can see both the mirrors and can see the traffic coming behind her and can drive carefully and properly. The warning is objects in mirror are closer than they appear. The warning is there because of the way we perceive distances. Our brains are programmed to estimate the distance of a familiar object from the size of its image. You see, our brains are such that if the image is smaller, we will think that the object is very far, and if the image is larger, then we think that the object is nearer. This is how our brain works. So, in this case, therefore, this warning that the object that we see, since their image is smaller, we are tricked into thinking that they are farther off, but actually they are not. So, since the image of the familiar object formed by the convex mirror is smaller in size, we are tricked into believing that the object behind us is farther than it actually is. So, therefore, this warning, because our brain tells us wrongly that these objects are farther off than they actually are, because their image is smaller. Why is the image smaller? Because convex mirror always forms a smaller image. Therefore, the image is always smaller, and the image is smaller gives our brain a hint that the object is very far, but actually it is not so in the case of a convex mirror. That is why this warning is there, that although you see the object or perceive the object as far, it is not, it is near, and you be careful. You must have seen such convex mirrors on traffic junctions. You see, when there are very big traffic junctions or there are sudden turns, then you do not know what is coming from the other side, and if a convex mirror is there, because of its large field of vision or field of view, it can see things coming from both the sides. So, it can warn the driver that something is coming, and therefore, you be careful. These mirrors are placed at the interjunction of traffic. If you have been to a large mall, you would have seen such mirrors there placed at various places. Why are they there? One, they can show a very large part of the establishment to the person who is looking at these mirrors. So, for example, indoors, especially in large buildings like hotels and hospitals, convex mirrors are strategically placed at sharp turns to avoid possible collisions. One, these mirrors are there, so you know somebody is coming from this direction or from this direction, and you are careful, you do not collide with that person. And they also serve as additional purpose, that is surveillance of shoppers. I mean, you go to shop and somebody somewhere, because of this mirror, is seeing how you behave, and if you are going to steal something, then it will be known to the person there. So, surveillance of shoppers, so that they do not indulge in pilferage and theft. In the next lecture, we shall again continue with this geometrical optics, and now we shall see the surfaces, spherical surfaces, which are separate two media of two refractive indices, and we shall derive this relation between object distance, image distance, and the radius of curvature of the surface. And we shall also see how we can trace the rays and form images, and we will see where these are actually used. They are used in lenses, and we shall see the basic forms of lenses in the next lecture.